I was right over here.
And then the other
All right, so today we're going to do some more Lewis dot structures. You have mastering due tonight. Seems like quite a few of you guys have already done it, so that's good. Mastering due Wednesday night. Nothing for Friday because it's mountain craziness, and I know even if I had stuff assigned, you wouldn't do it. So just makes more sense not to assign it, right? And we have fall break coming up pretty soon. Let's see, we have an individual quiz today. Let's ask the audience. How many people would like to take their group quiz on Wednesday? Okay, I won't even ask the other option. Yes. In that case, the group quiz is on Wednesday. Group quiz Wednesday. I need to get back up. And I will do my best to make class on Friday short for those who need to do costume changes and whatever else you do for Mountain Day. I always just stand on the sideline and cheer. Hopefully I can get some candy. That's all I want. So, all right, that's it, I think, unless anyone had any questions. Let's start off by doing some practice Lewis dot structures first, and then we'll get into the next bunch of slides. So these few things will get us talking about resonance structures and thermal charge. All right, so let's do so I'm going to give everybody like probably 5 minutes. You can work by yourself or check your answers with those who are sitting near you. But they have to write out the Lewis dot structures for these 3 molecules. Obeying the rules, right, where the least electronegative is in the center. I still have not fixed my periodic table, so let me put up a periodic table. Least electronegatives in the center. Hydrogens are always on the outside. Here, I put my periodic table. That's not terrible. Those are all the atoms you need. Carbon, oxygen, fluorine. You
put the one in the center that has the what?
Least electronegative.
It goes
in the middle. Yeah, so this is the most, this is the least. Oh, so yeah, 2 minus. If I have 2 minus on a molecule, what does that tell you about the total number of electrons? Add 2 more, right? So it means add up all the valence electrons and then add 2. Because the overall molecule has 2 more than it would normally have.
You put the which one in the middle?
Least electronegative.
Okay,
Yes,
yeah.
least in the center. And if you were not here on Friday, I have your exams still that you can come get at the end of class.
Put the periodic tables.
What was that?
Can you move the periodic table so
Mhm.
What were the other?
All right. So everyone did at least the first one, maybe two. Okay. All right, so let's look at this first one, the CCl4. All right, comparing carbon and chlorine, which one should I put in the center of the molecule? Carbon. All right, how many valence electrons does carbon have? 4. And then how many valence electrons does chlorine have? 7. I have 4 of those. Let's see, 28, 32. All right, so all together I have 32 electrons to put around. All right, so if the carbon's in the center, it must be hooked to the other chlorines, where a stick means the same thing as 2 electrons, right? It's a covalent bond, so 1 stick, 2 electrons. You can certainly write 2 electrons, but as you see, if you've done the mastering, it makes you do the sticks. So, all right, so how many electrons have I put in all together at this point? 8. Does the carbon want any more electrons? No. Where do I need to put all those electrons? Around the carbons, right? Or carbons, chlorines. Have I used up all my electrons? Is everybody happy? Everybody, okay, good. That was it. All right, let's do the next one. All right, now I have carbon and oxygen. Which one should I put in the center of the molecule, the carbon or the oxygen? Carbon. Okay. All right, so carbon's in the center, oxygens are around it. How many valence electrons does carbon bring again?
4,
Still 4. What about oxygen?
10,
Too many. Where's my periodic table?
6, okay, 10.
6. Yep, 6 valence. So it's going to be 4 plus 3 times 6, 18 plus 4, 24. Oh, plus 2. Sorry, plus 2 is 24. All right, so I have 24 electrons to put everywhere. If I know the carbon is hooked into the oxygen, how many electrons have I used of my 24? I've used 6, right? 2, 4, 6. Is the carbon happy as is?
No.
Not really. All right. What if I did, let's see. So I got 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. What's not good about that?
Oxygen doesn't have.
Oxygen doesn't have enough, but the carbons and the other oxygens are okay. What is a way that I can double count some electrons?
Double bond.
Double bond from who to who?
That last one.
What if I had drawn this like this? Is there any difference between those two molecules? Keep that in your mind. 5 minutes from now, we'll talk about it some more. Right, I could have put the double bond here, or I could have put a double bond to this one, right? Doesn't really matter which one. Keep that in your mind. We'll do our last one. Does anyone know what this molecule happens to be called in regular? Right, it's ozone. All right, do I know which oxygen to put in the middle? No, they're all the same. All right, so for sure, I know, it looks something like this. How many electrons do I have to place everywhere? Total. All right, so if oxygen brings 6, and there's 3 of them, I have 18 electrons. How many have I used up so far? 4. I got a long way to go. All right, how about we try, let's try this. All right, so the center one now has 8. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. No? What's wrong with that? Each of my oxygens have 9. No, okay. Plus I got this weird lonely electron. Okay, don't do that. Okay, what if I did... we'll do a double. I've now used up 18 electrons. How about that?
That one has to be.
This one has too many, right? Does this one have enough? No, okay. What if I did... Does that one look pretty good? Does everyone have 8? If I used up all the electrons, if I used up 18. Good, good. All right, we're going to do a bunch more, but those are just kind of our warm-up review problems. All right, so let's go back to thinking about this CO3 2 minus, and I had 2 different ways to draw it, and they were both, I mean, neither one were bad. Hold on, my notes are now all crazy out of order. Here we go. So in some cases, a Lewis structure does not adequately describe exactly what's going on in a molecule. right? There's more than one way to correctly draw it where everybody's an octet, everybody's connected correctly, you've used up all the valence electrons. The difference between the different options you have is the arrangement of electrons. But the connectivity between atoms is constant. So you're not reorganizing how they're connected, it's just you're redistributing the electrons in different orders. All right, so the one we just did, we had this. Right, all three of those, the oxygen and carbons are all hooked up in the same order. It's just where I put that double bond changed. So we use this double arrowed notation to say that these three structures are what are called resonance forms, which means they're connected in the same way, it's just where that double bond occurs changes. And all of them are occurring all the time. There's no preference between which structure is happening. We say the actual structure is somewhere in between all of these. So in these three structures, right, there's one obvious double bond and two single bonds. In reality, it's somewhere in between, right? All of them have a little double bond, all of them have a little single bond character because you can't tell them apart. So all three are occurring all the time with no preference between the three structures. It gets weirder when you get to organic. So this is like baby organic, where you draw the structure and double bonds occur and the double bonds can be moving and their electrons are here but not here, but I mean because I've written them down it means they're not actually there anymore. It's crazy, right? So let's do another example of a resonance structure. Let's do that'll be a good option. Let's do NCO minus 1. All right, looking at the N and the C and the O in our periodic table, which one should go in the center? Carbon. The answer is just about always going to be carbon. Goes in the center. C, N, O. Okay. How many valence electrons does nitrogen bring? 5. What about oxygen? What about carbon? 4. So I'm going to have 4 plus 5 plus 6. And what does this minus 1 tell me? Add one more. All right, so that's 16. All right, 16 total. All right, I can come up with 3 different ways to draw this molecule. Go ahead and take a minute or two and see if you can also write it 3 different equally good ways. And all 3 have the exact same starting thing. They all are going to start like that, and then we have to redistribute those electrons.
So you can reorganize.
Mm-mm. Nope. Can't reorganize them. They're stuck that way.
What matters the way you rearrange the oxygen and nitrogen?
Say that question again?
Because like I have like nitrogen, carbon, oxygen.
Oh, that's okay. Yeah, yeah. I just meant you couldn't do C and O
Yeah.
or NOC. It has to be. If they're going to be resonance structures, it means they all are stuck together in the same order. The next thing we do, we'll talk about something else. But resonance means they are stuck in the same order, just where the double bond is moves. Or triple bond, as the case may be. All right, has everyone gotten at least one structure? How about 2? Everybody got all 3? A few. Very good. All right, so we'll do number 1. What is a way I could get this oxygen to carbon?
Double bond both.
Double bond both? Sure. All right, so that uses up 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Is everybody happy? Yeah? Question first. Yeah.
Would it matter, like, the first one I did wasn't the double bond one, does it matter?
No, as long as you have all 3. All right. Okay. What's another way I could get the oxygen? Okay, I got triple bond oxygen. And then, okay, 1, 2, and then 1, 2, 3, 4, 5, 6. Is everybody? Okay, what's the third option then? Like the flop of it. How would I tell you, the reader, that they are resonance structures? I put the double arrows. Last thing, how do I tell you, the reader, that I had an extra electron added? You need to bracket the whole thing and tell me that you added an electron.
How do you do that on mastering?
Mastering is one of the buttons across the top. There should be a bracket thing, and you drag it around like a text box. You drag it around the whole thing. And then, again, at the top, there's like a plus minus button. You press minus, and you just click it anywhere outside the box. So, the little tutorial works you through how to do all that kind of stuff. So,
Shouldn't you be able to figure out the resonance structures? And if you're adding an electron, if you know how many electrons each element has?
yes, but I'm trying to do you a favor. I'm trying to do you a favor by saying I've already taken care of it. It's -1. So, I mean, if I gave you this, then you have to work through it. But if I gave you the 3 resonance structures, yeah, I'm trying to save you some work.
That if it ever has a charge on it, we need to note the charge.
Yes, the charge definitely tells you something important in terms of counting up number of electrons. So they're usually going to be negative, but occasionally you can have a plus something, and it means use one less electron.
You should be able to go from the resonance form to the NCO midpoint.
Yep. All right, good there? All right, what if you could move around how they're connected? So it is occasionally possible to write two different Lewis structures for a molecule where the atoms are rearranged. All right, so these are the cases where you haven't violated one of the Lewis structure rules. Everybody has an octet, you used up all the valence electrons, so you haven't done anything wrong, right? The structure's good. But the question is, how can you tell which is the better structure? Obviously, the answer is going to be formal charge because we're on the slide called formal charge. So formal charge will be the thing that tells you what is the better option. So formal charge I'm going to use charge in quotes because it's not like an ion. It's not holding on to the charge. It just means with the number of electrons around it, is it feeling like it has more than normal or if it has less than normal? So it's the amount of charge around a single atom. So we find the answer for formal charge mathematically. Now I'll write the formula, then I'll define what all the parts of the formula are. All right, it's a super fancy formula. They decided not go clever with their letters. All right, x minus parentheses y plus z over 2. All right, x is the number of valence electrons. All right, so just like we were saying, like how many electrons does carbon bring? 4. Actually, 6. So the number of valence electrons. Y is the number of electrons around a single atom that are not participating in a bond.
So that'd be the 4.
It's like the lone pair. So in the lone pair, it's the number of electrons in lone pairs around the atom. And Z is the number of electrons around an atom currently participating in a bond. All right, best Lewis structures have 0 formal charge. All right, so that's our optimum structure. If you can produce a structure that has 0 charge, everybody is totally happy. That is good. Next best has negative charge on most electronegative atom. All right, so if you can't make it 0, then you should have it so that any extra electrons are sitting on atoms that want extra electrons. All right, electronegative. So let's do some problems, and this will make more sense as we put it into practice. All right, here is my atom, CH2O. All right. All right, so those are my two different ways to draw it. Are they resonance forms? No, not resonance, because I have changed how they are hooked together. So it's two ways that are drawn, but they're not interchangeable. Like this is all H, like they're all in a row. This makes kind of a T shape. So they're not resonance structures. But we have to figure out which one is going to be the better way to hook them together. All right, so let's see. How many valence electrons should I be using? Let's see, 4 plus 2 plus 6, 12. All right, altogether I have 12 electrons. How many electrons have I used in this first structure? If you use 6, do the hydrogens want any more? No. All right, but I need to put more around the carbon and the oxygen. How do I need to fix that?
Could you also do triple bonds on carbon electron?
Let's see if I did that. No, because then I would have too many, like if I did this. That wouldn't be enough electrons. All right, 2, 4, 6, 8, 10. It's only 10. I mean, if I put the extra pair, then oxygen has too many. So, all right, let's figure out what the formal charge is on each of these atoms. So we're going to look at the formal charge of carbon, formal charge oxygen, formal charge hydrogen. All right, so using our equation from the previous page, how many valence electrons does carbon bring with it normally? 4. All right, how many electrons are around carbon that are not participating in a bond? Oh, question first.
Yeah, I'm just confused, like, why is that finished? If, like, hydrogen was 2.
Hydrogen can only ever have 2.
Oh, so it didn't say.
Yes. Everybody wants 8 unless you're hydrogen, in which case it only wants 2.
Okay.
Let's see. Okay, so how many electrons are around carbon that are not participating in a bond? 2. How many electrons are sitting around carbon that are participating in a bond? 6. All right, so I have 1, 2, 3, 4, 5, 6. All right, so 6 divided by 2 is 3, plus 2 is 5. So 4 minus 5 is -1. Okay? Is it 0? No. So already we're in kind of territory. All right. It may be okay. We'll see. It won't be, obviously, because I have 2 examples. I'm doing the bad example first. Then I'm going to do the good example. But play along with me. Suspend your disbelief. All right. What about oxygen? How many electrons does it normally bring with us? Okay, 6. How many electrons are sitting on oxygen that are not participating in a bond? 2. Takes way longer to say it than just do the math. All right. How many electrons are in a bond? 6. All right. All right, so 3, 2 plus 3 is 5, 6 minus 5 is plus 1. Have I put the negative charge on the more electronegative atom? Here's carbon, here's oxygen. No, right? The more electronegative atom is oxygen. But I said that carbon has the extra feel of -1.
So you want it to be negative?
I always want oxygen to be negative. I don't want carbon to be negative ever. Right? Because oxygen's more electronegative. So I want, if there's going to be a -1, it better be on the oxygen compared to the carbon. All right, let's look at option number 2. In my option number 2, I've used 6 electrons again. Hydrogens are happy, so we're going to do something like this. All right, it's the only way to use them up. All right, let's look at the formal charge of the carbon. All right, still brings 4 electrons with it. How many lone electrons are sitting on the carbon? 0. How many electrons are sitting in a bond touching carbon? 4 bonds, so 8 total electrons. You could just write 4. You could, if it's easier for you, this fraction is number of bonds. That's fine. Number of bonds. All right, so 8 divided by 2 is 4, plus 0 is 4. 4 minus 4 is 0. Oh, looking better. All right, let's look at the oxygen. All right, oxygen brings 6 again. How many lone electrons are sitting on it? 4. And then how many bonds does it have? It has 2 bonds, right? Oh, that is a much better structure. Everybody's much happier with a charge of 0. So if you were going to choose between the 2 of them, this would be the better option of the 2. Let's do one more. Let's do... Let's choose between these 2. We'll do... Let's see, how many electrons is that? 18 and 4. Is that right? 18 and 4? Okay. 18. All right, so you have 22 electrons to redistribute. Oh, no wonder why. Sorry. I was like, that won't work. So you have 24 electrons. 24 electrons to put everywhere. Take a mirror too and see if you can redistribute your 24 electrons. I made this problem up this morning, so I'm pretty sure it works. All right, in the interest of time, I'll go ahead and jump ahead. All right, so I could do this one by going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Is that right? Nope, I put one too many on there. Sorry. That has too many electrons. That's fine. Like, this is an option. Obviously, it's not a good option, right? It's not very good. That, oh, I guess I should do. That should have a double bond. That's why. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's still too many.
If you took out one between
So it's on one of the S's, the S,
just have too many.
the S on the right. That's double bond between carbon and oxygen.
Yeah, and just have two.
There you go.
The S is listed.
There we go. I told you I was winging it. It's not very pretty. All right, so let's quickly at least look at the carbon, the formal charge on the carbon. All right, so carbon normally brings 4. And then it has, let's see, 2 electrons sitting on it. And then 1, 2, 3, 4, 5, 6. So 3, so it has a charge of -1.
We can have different numbers if we have it drawn differently.
If you have it drawn differently, maybe different numbers. Yep. And if I look at formal charge oxygen, let's see, 6 minus, what is that? What is the issue here now? Yeah, the wrong one's negative. Right? Oxygen's definitely more electronegative, but it has a charge of 0. Things that's less electronegative has a charge of -1. Yeah. Is that not 1? Oh, sorry, +1. That's even worse. +1's even more catastrophic. Sorry, I was trying to do math quickly. 3, 5, 6 minus 5 plus 1. Way worse. It was bad before. This is actually much worse than I thought it was. That's a terrible structure. How about, you could put the double bond anywhere on this one. Right, I could have put the double bond between the carbon and the sulfur. That would be okay also. But looking at the carbon option, that's off to a stronger start. We'll do the oxygen. That also looks better. So of the two options, structure number 1 and structure number 2, what is the better way to hook them together? Number 2. All right, we will pick up there on Wednesday. You don't need a calculator for the quiz, but I'm going to put the periodic table because it's helpful.